Hey everyone, welcome back to Chem Story. Today, we're diving into a super helpful concept in chemistry, steric number and hybridization. Once you understand how this works, predicting molecular shapes and bonding patterns becomes way easier. So, let's jump right in and take a closer look. Alright, first things first, what exactly is the steric number? It's basically the total number of electron pairs around a central atom, and that includes both bonding pairs, the ones shared between atoms, and non-bonding pairs, which we also call lone pairs. So why does this matter? Well, knowing the steric number helps us figure out what kind of hybrid orbitals the atom will use and what the overall shape of the molecule will look like. In other words, it tells us how atoms arrange themselves in space and how that affects the way they bond in different chemical structures. Here's one important rule to keep in mind. When we're dealing with double or triple bonds, we only count them as one shared electron pair, not two or three. Even if there are multiple electron pairs involved, they're treated as just one region of electron density when we're figuring out the steric number. So how do we actually calculate it? There's a simple formula. Steric number equals the number of atoms bonded to the central atom plus the number of lone pairs. Let's try an example. Take ammonia, NH3. The nitrogen atom is bonded to 3 hydrogen atoms, and it has one lone pair. So the steric number is 4. The steric number doesn't just tell us about hybridization. It also helps us figure out the three-dimensional shape of a molecule. So let's go through some key patterns. If the steric number is 2, the hybridization is sp, and the shape is linear. A good example of this is beryllium chloride. When the steric number is 3, we get sp2 hybridization, which gives us a trigonal planar shape, like Bf3, boron trifluoride. With a steric number of 4, the hybridization is sp3, and that gives us a tetrahedral structure. A classic example is CH4 methane. If the steric number is 5, we're looking at sp3d hybridization. That gives us a trigonal bipyramidal shape, like PCl5, phosphorus pentachloride. And finally, with a steric number of 6, we get sp3d2 hybridization, which leads to an octahedral geometry. SF6, sulfur hexafluoride, is a great example of that. Now, here's something important. If a molecule has lone pairs, the shape might not be perfectly symmetrical anymore. That's because lone pairs take up space and push the bonded atoms slightly out of position. So, even though the hybridization might suggest one shape, the actual geometry can shift because of electron pair repulsion. You can see this in SF4, sulfur tetrafluoride, which has a steric number of 5, or BRF5, bromine pentafluoride, with a steric number of 6. Both of these molecules have lone pairs that distort the ideal geometry. Alright, that wraps up our look at steric number and hybridization. We've seen how the steric number helps us predict both the type of hybrid orbitals and the shape of a molecule. And by understanding how lone pairs affect geometry, we get a much clearer picture of real molecular structures. Thanks for joining me today, and I'll see you next time on Chem Story.